Welcome to Control System classes. The topic for today's class is effects of zeros in second order system and its equivalent time response analysis from electrical engineering talk. Let us examine a standard general second order function C of s by R of s is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. Let us assume the value of zeta belongs to an underdamped system and hence the roots are s is equal to minus zeta omega n plus or minus j omega t, and the equivalent s-plane representation is also shown here. By applying partial fractions and inverse Laplace transform, the expression C of t can be easily derived. So C of t is 1 minus e power minus zeta omega nt divided by root of 1 minus zeta square into sine omega dt plus theta. It means the final value is 1. How to obtain final value? By substituting the value of t as infinity. When you substitute t as infinity, e power minus infinity term will become 0. So this term is 0. My final value is 1. So my final value is 1. This exponential term is nothing but a transient component. What is the shape of transient component? It is taking a form of sinusoidal, but the sinusoidal magnitude is exponentially decaying as sine is multiplied with e power minus zeta omega nt. So initially we have a transient, it is exponentially decaying signal with a sinusoidal shape, and the final value is 1. The initial value can be calculated by substituting t as 0. When t as 0, my initial value was 0. As e power 0 was 1, the initial value is also 0. So this is the basic thing we need to revise in order to discuss about the effect of 0. So this is a general S-plane representation. Now to the original transfer function, let us add some more zeros. Let us take the 0 is located at the place s is equal to minus 20. It is far away from the imaginary axis and it is far away from the poles. As it is very far away, it will take the same shape as that of the original system, but it will have a small dip in the rise time. It will have a small dip in the rise time. Let us add a 0 at s is equal to minus 2 as it is nearby pole and also the imaginary axis, and hence it increases the initial overshoot. Also, it reduces the rise time further. So let us see the plot. This would be the plot if the 0 is introduced at s plus 2, or else we can say s is equal to minus 2. Let us introduce a 0 origin. So when a 0 is introduced at origin, it is nothing but the original transfer function is multiplied by a differentiator. So as we know, the differentiator will produce a change in magnitude whenever there are some changes, that is during transient. When the system is settled, when the system is taking a final value, the oscillations will reduce, and also the output C of t will become 0 if you multiply a differentiator with the original system. Now let us add the next case. Let us add a 0 at s is equal to 2. So when we added a 0 on the RHS, the component, this response will introduce an undershoot with an initial fast rise time. So the plot will be an initial rise, and then the graph will change to opposite side and it will have an oscillations, and then it will settle to a final value of minus 1. Then if it is introduced at plus 20, as it is far away from the axis, the contribution will, the shape will remain the same, but it will contribute a lesser initial magnitude. So the conclusion what we can make here is the addition of 0 on the LHS will changes the transient response, and also in the RHS it will changes the transient response. If it is an LHS, it will settles at a value of 1. If it is an RHS, it will settle at a value of minus 1 if I had normalized the gain. So let us look over the cases. Let us discuss how to derive the function C of t step by step when the given function is the form general second order system. So I'm not going to consider any zeros here. The general second order system is omega n square divided by s square plus 2 zeta omega ns plus omega n square. Here I'm going to assume omega n square as 2, 2 zeta omega n as 1. And then I'm going to interested to calculate my DC gain. DC gain is also called a steady state value. How to calculate the DC gain? By substituting S as 0. So when I had substituted my S as 0, I'm getting my DC gain value as 1. The next step is I should take the value of RFS. RFS value for unit step signal, it is 1 by S. So I'm substituting 1 by S and then I'm going to apply a partial fractions here. So I'm writing A by S plus BS plus C divided by S square plus S plus 2. On solving, I'm getting A as 1, B as minus 1, C as minus 1. Now you look at this equation. I'm interested to find C of t, but I cannot find C of t directly from this expression. For that, I'm going to modify the second term in order to apply a Laplace transform formula, inverse Laplace transform formula. So I'm going to rewrite the second term here. So I'm writing the term of the form. I'm expressing 1 as 1 by 2 and 1 by 2 component in the numerator, as well as in the denominator. I'm writing here s plus a the whole square. When you add root 7 by 2, root 7 by 2 whole square is nothing but 7 by 4, right? 7 by 4. When you add these terms all, 1 by 2, this term will become a square plus b square plus 2ab plus 7 by 4. When you add all the terms, it will remain the same. You will get s square plus s plus 2. Then again, it is not in the form to apply an inverse Laplace transform. So again, I'm going to modify the system. I'm going to modify the case. So I'm rearranging the second term further and I'm multiplying 1 by root 7 in order to apply the formula. So 1 by s on taking inverse Laplace transform will become 1. S plus a divided by s plus a whole square plus omega square. So a is 1 by 2, b is root 7 by 2. So it will become e power minus at into cos omega t. The next term is of the form omega divided by s plus a whole square plus omega square. So omega is root 7 by 2 and also a value is 1 by 2. And when we take inverse Laplace transform, it will become e power minus at into sine omega t. On applying all the formula, this would be the final equations. Now in this equation, substitute t as 0 to get the initial value. When you substitute t as 0, the initial value is 0. When we substitute t as infinity, this term will become e power minus infinity is 0. So the final value is 1. So in between 0 and 1, there will be a transient contributed by this term e power minus 0.5 t into sine and cos term. This term will contribute the transient response. The final value is 1. Now let us calculate the rise time, peak time and peak time for the given expression. Also we will cross check our damping. So in order to find the value of omega n square, so omega n or compare with the general second order transfer function. So omega n square is 2, omega n is 1.414. 2 zeta omega n is 1 and hence zeta is 0.35. It is nothing but an underdamped system. Omega d is omega n root of 1 minus zeta square. So it is damped frequency of oscillation is 1.323. When zeta is 0, for that case omega n would be omega d. As we have zeta as 0.35, here omega n is not equal to omega d. And Tp value is pi by omega d. Omega d is omega n root of 1 minus zeta square. So we can cross check our simulation results also. The peak time would occur approximately at 2.37 seconds. And also the peak overshoot formula is e power minus zeta pi divided by root of 1 minus zeta square. And the peak overshoot is 0.305. It means 1 plus 0.305. So peak overshoot is around 30.5%. So this is the response of the system without considering any zeros. Let us do the same procedure and let us consider the different adding with various zeros. Let us correlate the responses. So here, this is my first function. I have added a zeros here. S is equal to minus 2. The next term is minus 20, then plus 2, then plus 20. Now the 0 is added at origin. This is the case without considering any zeros. Now let us find the DC gain. So to solve the DC gain, substitute S as 0. So what you understood? The DC gain values are different when we substitute S as 0. In order to normalize the DC gain, why we need to normalize? Then only we can able to understand or we can able to obtain a clear results. So in order to obtain a DC gain to be a fixed value, I am going to multiply it by the zero values there. That is divide by the zero values. So s plus 2, it is a new term added. So I am dividing it by 2. Here 20 is a new component that will contribute, change the DC gain. So it is divided by 20. So for first 4 cases, I had modified by in order to normalize the function. For last two cases, it is not required as it is without zeros. This case is the zero is at the origin. Now do the same procedure as that of a previous case, and we got C of the functions. When you examine the C of the functions, all the terms for the first two terms, when it is in LHS, the final value is 1. When it is in the RHS, the final value would be -1. When it is at origin, there is no final value. The value is simply have exponential and sign. So we can able to come to the clear picture as at the origin, we doesn't have any final value. It will going to, as it is multiplied with e power minus term, all the values are going to decay when the time enlarges. For these two cases, when the zeros are in the RHS, the final value is -1. Here the final value is 1. How to obtain final value? By substituting t as infinity. And also we can obtain the initial value for all the cases. My initial value is 0. It is obtained by substituting t as 0. So we can able to come to a clear concept. It has all the component has transients. The initial values are 1. The final values are 1. When the zeros are in the LHS, the final values are -1. When the zeros are introduced at the RHS, the final value will become 0 when we have a 0 at the origin. That is, it will act as a differentiator. Let us simulate all the transfer functions. We have 6 transfer functions here. So I have simulated these transfer functions and I have verified the concepts with a MATLAB. So in order to do this, I have written a coding. So CLC, clear all, close all. These are all the basic commands to clear the command window functions, to clear the workspace, as well as to close the previous figure window and to open a fresh figure window with the executed, to print the executed output. So here I have used the command s is equal to tf of s in order to write the function in S domain itself. So I have written the S domain functions and also I had given a command line to mention where the zeros are introduced. And then also I have calculated the DC gain, and also I have obtained all the plot. I'm interested to see all the responses in the same figure window. So I have given a command step of all the transfer functions, 6 transfer functions, 20. The 20 corresponds to 20 seconds. The graph x-axis will vary from 0 to 20 seconds. And also I have given a legend to know which graph belongs to which zeros. When you execute the command window will show the output like this. So I had used a command display off. That's why I got the line DC gain. Inside the display command, what I had given, it will be directly printed. So DC gain of closed loop system for all the cases. So we can cross check our theoretical calculations what we had done. Now, so we had verified the DC gain from the output from the command window. Let us verify the graph with respect to the MATLAB simulation output. So let us examine the output. So in this output, we can able to see here, now 6 plots are printed here. 6 plots are printed here. The first plot is without any zeros. So without any zeros, the graph will increase smoothly. It has an initial oscillation as contributed by e power and sinusoidal terms, and then it settled to a final value. The second case is it is S is equal to -2. At S is equal to -2, it contributed a larger magnitude. It contributed a larger initial magnitude, and you can also cross check here. My rise time I get decreased. Initially, my rise time is large. My now rise time has now reduced. My rise time has reduced. Now let us look at the third case as when the 0 is introduced at s is equal to -20. So as it is far away from the imaginary axis, it is similar to the graph of without zeros. This blue represents the plot with differentiator, that is s divided by the general function, s into the general function. So initially it has an amplitude, it has undershoot, and then it becomes 0 as the response becomes constant value. These two plot represents the graph of the zeros which are in the RHS. So it creates an undershoot when it settles at -1. The previous one settles at 1 as we have normalized. So what is the final conclusions we can make? The effects of 0 will affect the transient response. It does not affect the steady state. It creates undershoot or overshoot. And the system is still stable, but it settles at 1. If the zeros are introduced in LHS, it settles at -1 as we have normalized. If the zeros are introduced in the RHS. If it is a differentiator, it will become 0. Thank you.